Next, we're going to talk about optimization. Optimization is the last topic in Unit 3. So Unit 3 originally included 4 topics, but we had to cut L'Hopital's rule because of this online transition. So now it is especially short. It only covers the first derivative test, the second derivative test, and this set of notes optimization. So hopefully that'll make studying for next week's exam a little bit easier. Before we get started on these examples, I think I'd like to sort of refresh on what we've done so far in Unit 3. So the idea so far in Unit 3 is this, that sometimes we're interested in finding the largest y value or the smallest y value possible on a given function. So we might have a picture that looks something like this. And maybe we're interested in trying to find the largest value that that function takes on, or the smallest y value that that function takes on. And what we notice about these local extrema is that if you're looking at a local maximum, like this one here, that's the place where our y value is the largest possible. Notice that this is a critical point for the function. In other words, the derivative of this function f at that point is going to be 0. And this is also a place where the concavity is negative. In other words, this is a concave down portion of the graph. So at this point, f prime is equal to 0. In other words, we're at a critical point, and f double prime is negative. So we have a concave down picture. And then conversely, if you're looking for a local minimum, so if you want to minimize the function f, then all that you need to do is you need to look for a critical point again, but you're looking for a critical point where the concavity is positive. So here you would be looking at a place where f prime is 0, so you're looking for critical points like we did in the first derivative test, and then you're also looking for the concavity to be positive. That's what we looked at in the second derivative test. So that's sort of a short summary of what's been going on so far in these notes. And in this section, optimization, we are going to be doing exactly the same thing. So the techniques in this set of notes are not going to be any different. We're mainly going to be applying the first and second derivative test to maximize or minimize very specific functions. So maybe we'll be looking at something like a profit function where the y value or the output value represents the profit and the input value might represent maybe the number of units that we want to make, for example. And then the first and second derivative test techniques will allow us to maximize the y value, or in other words, maximize the profit based on the number of units rather that we want to manufacture. So we would be able to find this maximal profit and the corresponding number of units that we should make in order to maximize that profit. Okay, so that's the idea in this set of notes. This is basically just the word problem unit for Unit 3. So let's look at the box up at the beginning of this set of notes. Here, this is just the general strategy that we're going to be applying in all of these problems. I will look over this strategy quickly with you, but feel free to come back and reference this. So you can pause the video and look over your notes if I go too quickly through any of the problems. But this is the strategy we'll use for all of these problems. So in step 1, it says you can make up some variables. Usually the variables that you'll define are going to be the variables whose value you want at the end of the problem. So for example, if we wanted to know the number of units we should make to maximize profit, then a good variable would be let x equal the number of units. So you'll make up a variable for all of the unknowns that you're actually looking for. And then we will look for relationships among those variables and use that to construct a certain model where we're trying to maximize or minimize a certain function on a given interval. And sometimes the interval is infinite, so you might be interested in just maximizing a function anywhere, and in that case we won't have to worry too much about that interval I. Steps 2 and 3 are basically just the first and second derivative tests. So they say that you want to find the critical numbers of f, so that's just finding the critical points, and then step 3 says that you want to find the absolute extrema of f. I'll talk a little bit more about that in a bit, but this just means that you might have several local extrema, So notice that throughout the first and second derivative test, we've been careful to say that a certain function's value is a local extreme. What we mean by that is, maybe let me draw a picture here. Let's say that this represented something like a profit function. Now notice that there are two hilltops here, but if we wanted to maximize the profit, we would want the y value here to be as high as possible, and that would only occur at this x value. So both of these would be local extrema. They would both be local maxes, x and y. Maybe I shouldn't use y here. I'll say x and z. Both of those input values would represent local maximums for the profit function, but x is the one that we would really want if we wanted to absolutely maximize the profit. So what's going to happen in this set of notes is occasionally we'll have a few candidates for the absolute extrema, and then we're just going to take all of the candidates that we find and plug them into the profit function, and whichever one of those gives us the bigger profit, that's the one that we'll take as our absolute extrema. So that's the idea behind steps 2 and 3 here. And then in step 4, you're basically just using that model to answer any of the questions that showed up in the prompt. So let's talk through this first example. It says you work at a farm that wants to build 3 identical corrals in a row against the side of a barn using 120 feet of fencing. No fence is needed next to the barn itself. What dimensions for each individual corral will maximize the corral areas? So here I'll sketch a picture because I think that's usually helpful in these problems. So this dotted line is supposed to represent the side of the barn, and we want 3 identical corrals. So I'll draw them like this. Pretend those are identical. Okay, and now what we're looking for is the dimensions for each individual corral. So it's usually a good idea to just give a variable name to each of the things that you're looking for. So if we want the dimensions, maybe I'll call this side x, so that'll be the width of the individual corrals, and then I'll call this side y. So what we're looking for at the end of the problem is x and y. And notice that because these are identical corrals, this middle side length would also be x, and this will also be an x. So all 3 of those side lengths are x's, and similarly all of these heights will be y's. So if we only have 120 feet of fencing in total, what we can see from this is we already have one relation between our variables, and that's that 4 times y plus 3 times x, that's one way of representing the total fencing. But we have another way of representing the total fencing, which is that we're told that we only have 120 feet total of fencing. So that's one relationship that we can use in our model. But what we need to know first is, what are we actually trying to maximize? So here we're maximizing the corral area. So the setup to these problems is, first, usually after you've found the variables that you want in the model, you define the thing that you want to maximize. So here we want to maximize the area of each corral. So that would be this area A, and that would be x times y. But in order to continue using this first derivative test, we need A to be a function of just a single variable. So I don't like the fact that this is an x times a y. I want this to be a function of x so that I can take the derivative and look for critical points. But thankfully we can use this relationship that we found a second ago to solve for y and turn this function a into a function of a single variable. So notice that if I subtract 3x from both sides, I get that 4y is equal to 120 minus 3x. And then dividing both sides by 4, I get that y, the height of each of the corrals, has to equal 120 minus 3x divided by 4. Or if you'd like, we can divide each of the terms in the numerator by 4. This would just be 30 minus 3/4 x. So now that we know the value of y in terms of x, we can come back over here to the function a, and we can rewrite this y as a 30 minus 3/4 x. And now we're in business because we just need to take the derivative of this function a and maximize it in terms of x. So now we can apply this first derivative test technique that we've been talking about. If you'd like, you could, in taking the derivative, just use the product rule, but normally I like to distribute this so that I don't have to worry about any complicated rules. So I would distribute this x so that we get a 30x minus 3/4 x squared as this function a. And now this is what we're trying to maximize. So I want to know what x value would I need to plug in order to make a as big as possible. And that's what the first derivative test and the second derivative test are designed for. So we will go through the application of those tests. The first step in the first derivative test is just to compute this first derivative. So that would be 30 minus 3/4 times 2x. Or if you'd like, you can cancel this factor of 2 with the factor of 4 down here to get a remaining factor of 2 in that denominator. So this would be a 30 minus 3/2 x. So that's the first derivative. Now we look for the critical points. The critical points, remember, are where the derivative is equal to 0. So we're going to take that derivative that we just found a second ago and we're going to set it equal to 0. And then we solve this equation by finding all of the x values that we could plug in that are solutions here. So in this case, because this is just a linear equation, I can rearrange to solve for x. So I'll get 30 is equal to 3/2 x. And now if I multiply on both sides by 2/3, then on this side the 3's cancel and the 2's cancel, so I just get x. And on the left side, I'll get 2/3 of 30, which is 20. So I get 20 is equal to x. Now, in this case, our only critical point is just 20. So we have a pretty good idea that this is going to be the local max. But to verify that it's a local max, you could use the second derivative test. The second derivative here is a double prime, so maybe I'll come back up here. If a prime is 30 minus 3/2 x, then a double prime is equal to the derivative of this expression, which is negative 3/2. And notice that that's a negative number. So in other words, this point 20 is a critical point, but it's also a critical point that has a negative concavity. So that would look like this, and therefore negative 20 represents a local maximum. It's actually true more generally that if you're trying to maximize something that looks like this quadratic, any quadratic graph is going to look something like this or like this if the concavity is positive, and therefore it's going to have a unique maximum or a unique minimum. So this will represent the unique maximal value for the function a. But remember, what we were looking for is not just the x value that maximizes at the area. We also wanted to know what dimensions, so we need to know the height as well. But thankfully, this part is pretty easy. Once you have the x value that you want, in this case, x is equal to 20, we can find the y value by just plugging in what we found earlier. So we saw earlier that y is equal to 30 minus 3/4 x. But now we have our x value. So if I plug in my x value of 20, then I can find the corresponding y value. So I'll just do that down here. Y is equal to, what was it, 30 minus 3/4 x. The x is 20, which gives us a y value of 15 altogether. So what I like to do at the end of these problems is I would rewrite this in terms of the original prompt. So I would say that my answer is 20 feet by 15 feet. So those are the dimensions of the corrals with maximal value, or maximal area, rather. Okay, and in the next